Okay, so welcome to this video lecture. Doing this because we have, I won't be here today. I'm at a conference today and I didn't know about it, so I decided I didn't want to skip a day of lecture. I'd rather have you guys get going so that next week we can launch, or we can drop a pumpkin out the window. So I'm trying to speed things up a little bit, even though I'm going to be out. This is one of the last things we did on Thursday. We were talking about a pumpkin falling from rest. And as you can see here, this should be very similar to what you have drawn. The velocity of the pumpkin as we go from time 1 to time 5 starts at no velocity, and the velocity increases each time and it always points towards the ground. The acceleration, on the other hand, this object is in free fall, and free fall means that the object will have a constant acceleration because of gravity or due to gravity. The acceleration, as you can see, stays the same each time, as represented by the magnitude of the acceleration vector. So, as far as a conclusion goes, here is what we could say. For a dropped object, A, the acceleration, is constant because A is equal to G, and it points down. In other words, the acceleration does not change as the object falls, and it is directed down. Remember, the acceleration is a vector. V, on the other hand, V increases, it gets bigger as the object moves towards the ground, and V is directed toward the ground. Okay, that's a good summary of what we have as the object falls from 1 down to 5. And again, 5 is right before it hits the ground. The object hasn't hit the ground yet because we know it's still moving. It's right before it hits the ground. So this is a conceptual picture of how the velocity changes over the course of the fall and how the acceleration doesn't change. And we saw this yesterday when we did this, when we actually used the motion sensor to get this data ourselves. What I'd like to do now is show you how we could use our kinematics equations to determine not only, let's say the pumpkin takes 2.4 seconds to hit the ground, not only the final velocity of the pumpkin, also the height from which it was dropped. So let me zoom in. We'll take a second to do that. Okay. So we're looking for the final velocity of the pumpkin right before it hits the ground, and also the height from which it was dropped. So the two things we're going to look for are VF, our final velocity, and also the height, which is a distance, so I'll represent that with D. Now the things that we know this pumpkin was dropped from rest. That means the initial velocity must be 0 meters per second. We know that the time the pumpkin dropped for is 2.4 seconds. And this usually won't be stated in the problem, but you are supposed to infer, since this object is in free fall, we know the acceleration. We know that it is 9.81 meters per second squared. Now, we can know these three things. We can use any of them to, we can use some equations to find the final velocity and the height. Let's do the final velocity first. I'm looking for VF. I don't know distance, so it's not a good idea to use an equation with distance in it. I know VI, T, and A. That says we should use the Phi equation. Okay? Because I know all three of these things, and I'm looking for the final velocity. Matter of fact, I know the initial speed is 0, so I'll cross that off like so. That's enough signal that you know that it's 0. You know the acceleration is 9.81 meters per second squared. You know the time is 2.4 seconds. And if you calculate that out, you should end up with an answer, or a final speed, of 23.54 meters per second. That is the final speed right before the pumpkin hits the ground. Okay, just before. We don't usually take into account the speed when the pumpkin is on the ground, because at that point the pumpkin's undergone a different acceleration. We don't need to know that. We do need to know the distance, however, the height from which it was dropped. In other words, the distance it traveled from where it was dropped to the ground. Now I know I actually have a couple choices of equations I can use. I'm going to stick to the one that involves the three things I was given. I'm looking for distance. I know initial velocity, time, and the acceleration. That means I'm going to use this equation. I could use the other one that we haven't used yet, but I'm choosing to use this. D equals VIT plus 1/2 AT squared. Again, I know the initial velocity is 0. I can cross off this entire term. It doesn't matter what this t is, because anything times 0 is just going to be 0. That entire term goes away. It's just 0. Now I just need to plug in. I have 1/2. Acceleration, once again, is 9.81 meters per second squared. The time is 2.4 seconds, and that needs to get squared. Notice there's a difference between this squared that's on the units here, and this squared that's literally squaring this number, okay? I have to do something with this squared. I need to take this into account. I need to square the 2.4. This squared is just part of a unit. I don't have to do anything with that. So, what ends up happening is I do 1/2 times 9.81 times 2.4 squared. The answer should come out, and I encourage you to check this on your own. The answer should come out to 28.25 meters. Now, how tall is that? Okay, is that taller or shorter than the roof of the 3rd story, okay, on the school building here? Turns out that's almost twice as tall, which sounds weird. How could this pumpkin, being dropped for just 2.4 seconds, move over a distance of twice as tall as a school? That's like 80 feet. 2.4 seconds is a lot longer than you think, okay? 2.4 seconds is like, if you start now, 1, 2, stop. That's about 2.4 seconds. Something that gets dropped can fall a long way in that period of time. So these answers are both legitimate, and they should both make some sense. Now, what I'd like to do is, let's leave this example. We're going to go to a new sheet of notes, which you should have gotten. This will be a second situation with free fall. But instead of something just falling straight down, in this time, we're going to talk about an object that is getting launched upwards from the ground. We're going to talk about some of the things that we can determine from this. So, here's a picture representing the position at different points in time of some object that gets launched straight up in the air. It's not a straight line, it's moving over just so we can see this is when, these are the points when it's going up, it hits the peak, then it comes back down. For the first point in time, the velocity and acceleration vectors have been added. We're going to draw the velocity and acceleration vectors for the rest of the points first, then we're going to answer some of these questions. So let's flash back to a couple weeks ago, maybe last week, I can't remember exactly when we talked about this, when we talked about what happens if your velocity and acceleration point in opposite directions. You should recall that if this happens, then that means that the object should be slowing down. In other words, the next velocity is not going to be nearly as big. Maybe like this. That'll be the velocity. However, after this object gets launched, okay, this object gets launched and comes back down, once it's launched and it's not in contact with the ground or the launching, whatever launched it anymore, it's in free fall, which means the acceleration is going to be 9.81 meters per second squared directed towards the ground, and that will never change. So our acceleration vector for this second one should look exactly the same. Okay, I've still got, moving to the third dot, I've still got velocity and acceleration in opposite directions. Make that a little longer, make it look a little better. Okay, I've still got those two in opposite directions, so I should get an even smaller velocity up here. And again, the same acceleration on its way down. When we get to the very peak of the motion, if you were to toss something up, okay, like this, there is one instant in time at the very peak where the object is not moving. There is actually no velocity. However, the object is still in free fall at that point, okay? There must still be an acceleration. And if you're getting confused by that, think of it like this. If it was at the peak and there was no velocity and no acceleration, that would mean it's not moving and the velocity is not changing. So it would just stay up there. I don't know about any of you, I have never, ever in my life tossed something up and had it at its peak just hover there. It doesn't happen like that. It must be true that there is still some acceleration at the very peak. On the way back down, let's get this out of the way. Let's fill in our acceleration since we know by now that that is not going to change. The acceleration is going to be the same throughout. And here it is right before it hits the ground. I know it looks like it's touching, but trust me, this is right before it hits the ground. Let's talk about what happens to the velocity in this case. We've started moving down, So the velocity is now going to point downward. And in kind of a neat trick, the velocity is going to have the same magnitude as it did on the matching point as it's going upwards, but the velocity has the opposite direction. And we can prove this. We can actually show this, okay? Not right now, but we'll show it later. When you've got two points, when you've got something going up and coming down and it passes the same height, the velocity at those two heights, okay, once one's going up, once one's going down, the magnitudes of those velocities are equal, however, the directions are opposite. So, to talk about the velocity here, this is the same magnitude velocity as you have here, it's just in the opposite direction. Now, again, a couple weeks ago we talked about how the velocity and acceleration, if they're in the same direction, that is an object that's speeding up. So we should get a bigger velocity for this second point on the way down, and the biggest velocity for this third point on the way down, since we're still going to have something that is speeding up. Okay? If this doesn't make a ton of sense, maybe rewatch this again, see it a couple of times, and it should, you should be able to reason your way through this. How the velocity changes, how the acceleration does not change. Okay? We're going to answer a couple questions about this before I cut this video off and go to the next one. First thing we're going to talk about is if this object is in free fall at these different points. Before it's launched. Well, before it's launched, it's on the ground, and something's got to launch it. So before it's launched, this can't be in free fall.